Welcome to this module of this course Computer Aided Power System Analysis. Up to the last class, we have discussed about the formation of the bus admittance matrix of any general large power system. But in that formulation, we have not considered the mutual impedance between the lines. So, here in this lecture as well as in the next lecture, we would be looking into the fact that how do we take into account the mutual impedance between any two lines into account while forming the bus admittance matrix. So, what we are trying to do is as actually follows. Suppose I do have, so this is let us say bus 1, this is bus 2, this is bus 3, and let us say there is one transmission line between all these buses, and suppose that these two lines has got some mutual impedance connecting between these two lines. So, now what we are trying to do is as follows. Now, suppose I do have let us say bus U, bus V, let us say bus X, bus Y. So, it is bus U, bus V, bus X, bus Y. Between U and V there is an element connected, between X and Y also there is an element connected, the current through this element is let us say I C, the current through this element is I D, the impedance of this element is Z C, the impedance of this element is Z D, and these two elements are interconnected, or rather they do have a mutual impedance between them as Z M. Let us say that the current which is being injected here I U, I V, these are all complex quantity, this is I X, this is I Y. So, this is the setup. So, what we are actually trying to do is essentially we are trying to formulate or rather find out an equivalent circuit between bus U, bus V, bus X and bus Y, such that after we form the equivalent circuit connecting all these 4 buses, we would be able to apply the standard rules of forming the bus admittance matrix. So, essentially that is our goal. So, to do that, so now let us see we have that, and let us say that this voltage across this is V C, voltage across this element is let us say V C, V C, voltage across this element, and voltage across this element is V D, V D. So, we can write down V C, V D is equal to Z C, Z M, Z M, Z D into I C, I D. These are all complex quantity, because after all V C would be Z C I C plus Z M into I D, and also V D would be Z M I C plus Z D into I D. So, then therefore, I C I D would be Z C, Z M, Z M, Z D inverse V C, V D. Now, it would be, so this would be equal to 1 by Z C Z D minus Z M square into ZD minus ZM minus ZM ZC into VC VD or in other words, so we can write IC ID is equal to YC YM YM YD VC VD, where YC is given by ZD by this, delta Ym is given by minus Zm by delta, and Yd is given by Zc by delta, where delta is equal to Zc Zd minus Zm square. Now, from this circuit we can write down that IU, IV, IX, IY is equal to if I try to represent it all this injected current IU, IV, IX, IY in terms of this branch currents. So, we get some matrix. Now, what this matrix? Clearly here IU would be equal to IC and IV would be equal to minus IC. Similarly, IX would be equal to ID and IY would be equal to minus ID. So, then therefore, IU would be equal to IC. So, it is 0 1 0. IV is minus IC, so it is minus 1 0, IX is equal to ID, so it is 0 1, and IY is equal to minus ID, it is 0 minus 1. So, let us say this is matrix C, some matrix C into IC ID. Where matrix C is this matrix 1 0 minus 1 0 0 1 0 minus 1. Also, VC is equal to VU minus VV and VD is equal to Vx minus Vy. So, then therefore, if I write down Vc Vd is equal to, we have something called here Vu, Vv, Vx, Vy. So, it would be something like this. So, Vc is equal to Vu minus Vv. So, it would be 1 minus 1 and others would be 0, and Vd is equal to Vx minus Vy. So, it will be 0 0 1 minus 1. So, we can clearly see that this matrix is nothing but transpose of this matrix C. So, this row this column becomes this row and this column becomes this row. So, then therefore, we can write down that Vc Vd is equal to C matrix C transpose Vu Vv Vx Vy. Now, we have IC is equal to, now we have IC ID is equal to this. So, now we would be, let us say that this is equation 1, we should set equation 1, we should say that this is equation 2, and we should say that this is equation 3. Suppose from equation 1, IC ID is equal to YC YM YM YD VC VD. Now, I pre-multiply everything by the matrix C. So, I pre-multiply everything by matrix C. So, then I get, pre-multiplying everything by matrix C, I get C into IC ID is equal to matrix C into YC YM Now, in this equation we will now put equation 3. So, this is, let us say this equation 4. So, substituting equation 3 into equation 4, we have that C into IC ID is equal to matrix C and then it is VC VD, and VC VD is C transpose this. So, is C transpose VU VV Vx Vy. Now, C into IC ID. Now, from C into IC ID is nothing but IU, IV, Ix, Iy. So, if I utilize equation 2 here, so then therefore, we have IU, IV, Ix, Iy equal to matrix C YC YM YM YD C transpose VU, all are complex quantities, VU VV Vx Vy. So, this is utilizing equation 2. Now, we have to look at that what is this matrix C into YC YM YM YD C transpose. So, now let us look at now C into YC YM YM YD C transpose. So, that would be equal to C matrix is 1 0 minus 1 0, this matrix. So, this is 1 0 minus 1 0 0 1 0 minus 1. This is y c, y m, y m, y d, and C transpose matrix is, this is just 1 minus 1 0 0 0 0 1 minus 1. So, what I would get? So, I would get here from here 1 0 minus 1 0 0 1 0 minus 1, and this would be y c minus y c, y m minus y m, it would be y m minus y m, y d minus y d. So, this is a 4 cross 2 matrix. So, this is a 4 cross 2 matrix, and this is a 2 cross 4 matrix. So, then therefore, their product would be a 4 cross 4 matrix, and this product would be, so it is y c minus y c, y m minus y m. This is minus y c plus y c minus y m, y m. This plus is not required. This plus is not required. Then what we have? We have y m minus y m, y d minus y d. Then we have minus y m, y m minus y d, y d. So, this is the matrix. So, this is the matrix. So, this matrix is this. So, then therefore, what we have is, then therefore, we have is, therefore, we have I u, I v, I x, I y, is equal to, so this big matrix 4 by 4, and it would be v u, v v, v x, v y, sorry, this would be all complex quantity, this would be all complex quantity. So, y c minus y c, y m minus y m. So, it is y c minus y c, y m minus y m. minus yc, so it is negative minus yc minus ym. Then ym minus ym, yd minus yd, so ym minus ym, yd minus yd, this is minus ym, this is just the negative of it, minus ym minus yd. So, what we got? We got bus admittance matrix connecting the injected currents. So, what we have got? So, you see here what I have got IU, IV, IX and IY, these are nothing but the injected current at bus U, bus V, bus X and bus Y respectively. And this voltage is VU, sorry I should have mentioned either, this is voltage VV, this is Vx and this voltage is Vy. So, I have got these voltages Vy, Vv, Vx and Vy. So, what we have got? We have essentially connected this injected 4 injected currents IU, IV, Ix and Iy with these 4 bus voltages Vu, Vv, Vx and Vy. So, then therefore, so it may appear that we have done our job, but the problem is now, so then therefore, this is nothing but the bus injected current, this is the bus voltage vector and this is the bus admittance matrix as far as these 4 buses is concerned. Now, it may appear that we have done our job, but the point is we really cannot utilize this because this particular bus admittance matrix cannot be directly incorporated into our normal standard bus admittance matrix. So, then therefore, we need to do something else. So, what we will do is, so now we will now utilize these equations and we will go through this. Now, here there are, so IC, ID, VC, VD, so now let us write down these equations. So, now these equations are, so now we have to write down the equations are IU is equal to YC VU minus YC VV plus YM Vx minus Ym Vy, these are to this we simply add Ym Vu and then also subtract Ym Vu. So, what we get is Yc Vu minus Yc Vv plus Ym Vx minus Ym Vy plus Ym Vu and minus Ym Vu. So, we have simply added and subtracted Ym Vu from these expressions. So, we got this. So, from here what I get, I take Yc as Vu minus Vv from these two terms. Then we take Ym Vu, this minus Vy and then minus Ym Vu minus Vx. So, this is the expression of IU. So, then if this is the expression of IU, so then what we can have that for this, so suppose so now we have got I V X Y. So, this is bus U, this is bus V, this is bus X, this is bus Y, and we have got injected current I U. And now, so now we can see that this injected current I U is actually constitutes of these three terms. So, if we can represent these three terms by means of some equivalent impedance or admittance, so then therefore, we can express this first row of this equation, or rather first row of this particular matrix relation by an equivalent circuit. So, now let us see how do we do this. So, from this, so I have got IU. So, now if I put YC here, YC here, and then I put VU minus VY. So, this is I put here YM, this is YM, and between these two I put another admittance minus Ym. So, now what do I have? This current which is entering this bus is constituting of three currents, this current plus this current plus this current. This current is obviously Vu minus Vv into this admittance. This current is obviously Vu minus Vy into this admittance, and this current is actually Vu minus Vx into this y, and this is precisely this particular relation shows. This current is nothing but Yc into Vu minus Vv. This current is actually nothing but Ym into Vu minus Vy, and this current, this third current, is nothing but equal to minus Ym into Vu minus Vx. So, then therefore, what we have done, that we have represented the first row of this matrix equation by an equivalent circuit. So, then similarly, we can also represent all the other rows of this equation by some other equivalent circuit, and then we have to actually add those four equivalent circuits together, and we have to arrive at the compact equivalent circuit representing this particular network. So, this we will do in the next lecture. Thank you.